Good morning, class. Hope you're all doing great. Happy Friday. And today we're gonna focus on concept questions, but I do want to give you a little bit of knowledge about some study materials that I posted since last time. So I got a request to look for and post some study guides for the final exam, and I did that. And I'll show you where to find this. So if you go to Sakai, and resources, so the exam 1, 2, and 3, for preparing for the final exam, there's some new material which deals with rotational mechanics, the stuff we've been talking about for the last few weeks. But exam 1, 2, and 3 solutions are posted here, and those are terrific study guides. All right, for preparing for the final exam. And then of course, there's all the slides here, clicker questions, the equation sheet that you'll have on the final exam. And then I posted some study guides. So these are a hodgepodge of study guides for material as I presented it over the years. So the exam 1, 2, and 3, and even exam 4 designations don't necessarily line up perfectly with the way you were tested on stuff this semester. And with final exam review guide, rotational mechanics and fluid mechanics, we just ran out of time this semester to talk about fluid mechanics. So that material is not on the final exam, obviously. But the material on rotational mechanics, except for we haven't talked about angular momentum. I'd like to talk about that on Monday with you because it's such a neat topic. But I don't think I'll be asking you any questions about angular momentum. Maybe one concept question about angular momentum on the final exam. But these other study guides are even for, not even sure if the chapter numbers line up anymore, but these are summaries of the material throughout the semester. So hopefully this is helpful for you guys. And like equations, when I write these study guides, I don't write out equations. I just say what the equations are in words. So like you find a definition of kinetic energy, and I'll say kinetic energy is 1/2 an object's mass times its speed squared. That's in word form what that formula is. Okay. So let's take a look at, again, the homework isn't due until next Friday now. But on keyboard. All right. Okay, but this I want to show you this last problem. Oh, I emailed about this problem being incorrectly coded. I haven't heard back yet, but it's worth 0 points. So it's a really good problem, but you won't be able to tell if you got it right or wrong. You know what? I feel like we should set that problem up so I can show you how you do it. So we'll do that. But this video is just really neat. Can I skip ahead? It's gonna make me do all these steps.
I've got to say, that was an excellent shot you made.
I'm just gonna select the answers.
That was another great. So I
too far.
think we can It's a great show.
Totally awesome.
I loved watching it in slow motion when it was spinning. How do you like that video footage?
Excellent.
pretty good.
Okay, so here's
They went to the same height.
Shh. Here we go. All right. I'm gonna turn on the desktop audio here. So the mic is on too. I'm gonna mute the mic so you can just listen to the video for a second. But I'm gonna play this video for you. Oh shoot. And so what you have is on the left-hand side is this block of wood, and it was shot by a bullet right square in the middle. So it rises but doesn't rotate, and this one was hit by a similar bullet, exactly same size and cartridge, and but it's hit along the edge here, so it rotates as it rises. But the thing to notice is that they rise to the exact same height. So really, all right, let me mute my mic and look at that, the exact same height. And so which of these blocks of wood has more energy? It would be this one, because it's moving linearly, so it has linear kinetic energy, but it also has rotational kinetic energy. So the way to understand why they rise to the same height is to think about momentum. So if momentum is conserved, linear momentum is conserved, the momentum of the bullet before the collision must equal the momentum of the block and bullet combination after the collision. And for that reason, the blocks are going to move linearly in the same distance because linear momentum is conserved. Anyway, you know, as you work through this, it's a neat experiment that combines the topics of linear momentum, translational kinetic energy, rotational kinetic energy, and all into one problem. And it's also impressive that they were able to pull this experiment off and actually conduct it. So obviously they're using some high-speed cameras there to take video of the block as it's rising and rotating. All right, so let's take a look at this problem. Again, you won't get it correct even if you get the correct answer, but let's take a look at how you would set up a problem like this and solve it. We'll go over to, here we go. Yay. All right. So in this problem you have a pulley, a wheel, that is actually two parts. So, well, it's one solid object, but it's got two different pulleys. So this wheel has it's actually two wheels, but they're connected. So this one's got, oops, oh my gosh, here we go. So this one's got a mass wrapped around it, so there's a string wrapped around it, and the mass hanging down on this side. Call that M2. And the outer wheel has a string wrapped around it and a mass hanging down on this side called M1. So the weight of these masses, call this R2 in this distance R1. Okay, So the weight of these masses are going to be their respective masses times the acceleration due to gravity. So these are forces that are pulling down on the system, like so. So what you'll have is mass 1 is exerting a force at a distance equal to r1 away from the axis of rotation here in the middle. Here's the axis of rotation. And that's going to generate a torque that has a counterclockwise sense. It's going to tend to want to make this wheel rotate counterclockwise. On the other hand, mass 2 is exerting a force on this inner wheel right there, and that's going to generate a torque that will tend to want to make the wheel rotate clockwise. So mass 1 will generate a torque, call it tau 1. Mass 2 will generate a torque, call that tau 2. And so we got to define one of these directions as positive and the other as negative, and that's, you know, the vector nature of torque. So let's call this direction positive. The clockwise rotation is positive. So the way to approach this problem is that what matters isn't the individual torques, but the sum of the torques. So that net torque is going to equal tau 2, which is positive, minus tau 1, which is negative. And net torque is equal to rotational inertia times angular acceleration. Alright, so these are vectors, but I've already taken the direction into account right there. So we can drop that. But alpha is a vector too. So if alpha turns out to be negative, that means this thing's rotating, accelerating counterclockwise. If alpha turns out to be positive, that means it's accelerating clockwise. Because I defined what that means up here. Okay. So the torque, so tau 2 is going to have a magnitude equal to the force exerted by mass 2 times crossed into that distance r2. So these forces are applied exactly perpendicular to the wheels. You know, so there's sort of an axis that goes through everything here, and the forces are applied right there at a point that's tangent to the wheels because everything's hanging vertically down. So when we write this out, the cross product is sine theta. The angle, because everything is perpendicular here, is 90 degrees. So sine theta becomes 1. Just goes away. Okay, and then the torque exerted by mass 1 is its weight crossed into R2, which is going to equal which is again 1. So when you write out the net torque, what you have is torque 2 is equal to that force F2, which is the weight of mass 2, times R2, minus the weight of mass 1 times R1, and that's going to equal the rotational inertia times alpha. So you have this equation that governs the dynamics of what's going on. So in this problem, they ask you to find, with this you're given here, this is the things that you're given. You're given this, of course you know that, you're given this, you're given this, you're given this, you're given this, you're given this. So you're given all those things, which means you can solve for alpha. And then once you have alpha, you can figure out the tangential acceleration of mass 1, because it's just equal to alpha times the radius, r1. And you can find the tangential acceleration of r2 in the same way. Okay, so that's how you would set up that problem and solve it. The there's multiple torques in play, causing an angular acceleration. So this is like a modified version of the Atwood's experiment. Remember the Atwood's experiment, except in this case, the thing that is rotating is not massless. Remember when we did the Atwood's experiment, we had the assumption that the pulley was massless, and the reason we use that assumption is because that means we are saying we can ignore the rotational inertia of the pulley itself. So it doesn't take any energy to get the pulley spinning. But in the real world, that's not the case. So all right. So again, this problem, it's worth knowing how to work it out. It's important to know how to work it out, even though the WebAssign is miscoded, as far as I know, unless there's something I'm missing here, and won't mark your correct answers as correct. But that problem's not worth any points. All right, gang, let's do some concept questions now. Do you remember how to do this? So here's my poll on Poll Everywhere. pollev.com/JeffreyGroff336 or text JeffreyGroff336 to 37607 to join the poll, which is now active. All right. pollev.com, JeffreyGroff336 or JeffreyGroff336. Text JeffreyGroff336 to 37607 to join. All right. So some of you are already on. Great. All right, you ready? I'll wait 30 seconds here. How does the total results fluctuate? It goes up and then it comes back down. That's so weird. How can you rescind your vote? That's so weird. What do you guys are crazy. All right. Here we go. All right, hold on. There we go. All right. Rotational mechanics. All right. I love this question. Bonnie and Clyde are bunnies. And Bonnie is sitting near the outside of a merry-go-round, the outer rim. And Clyde sits midway between the center and the rim. The merry-go-round completes one revolution every 2 seconds. 1 revolution every 2 seconds. Clyde's angular velocity is same as Bonnie's, twice of Bonnie's, half of Bonnie's, a quarter of Bonnie's, or 4 times what Bonnie's is. So there actually is an undo option. That's crazy. Oh, okay. I'm going to clear the responses and let you vote again, all right? Because, oh my gosh, it's all over the place. And I'm not sure if that's because I didn't clear responses before. So I'm going to clear and then vote again, okay? Go. Nope, not my imagination. You guys are all over the place. All right, so it's like a uniform. Oh, no. Okay, you guys are converging now. All right. I feel a little better now. You're starting to converge around one of the answers. Okay, So, can you figure out what the angular velocity is? 1 revolution every 2 seconds. So, that's a measure of angular speed, revolutions per second, but we want units of radians per second. So if you complete 1 revolution every 2 seconds, you go 2 pi radians every 2 seconds. So that's pi radians per second. So 3.1415 radians per second is the angular speed. And the question is, well, does that answer depend on where you are? And the answer to that question is no. The angular velocity of a point on this wheel, now if you're here where Clyde is, or you're here where Bonnie is, it doesn't matter. You're on the same wheel. So Clyde's going to make 1 revolution every 2 seconds, and Bonnie's going to make 1 revolution every 2 seconds. And if you were Bob, the bunny, and sitting right here, you'd make 1 revolution every 2 seconds. So the angular velocity of a rigid, solid object doesn't depend on where you are on that object. All parts of a wheel rotate with the same numbers of radians per second, or revolutions per second. All right? So only half of you got that right, but that was your favorite answer. But let's go to the next question. All right, the angular velocity omega of any point on a solid object rotates about a fixed axis is the same. Both Bonnie and Clyde go around 1 revolution every 2 seconds. There's a follow-up question here. Let's see if you know the answer. Let me clear the... Well, no, it's not a poll question. Which way does the omega vector point? So this would be an application of a right-hand rule. And so how could we do that? Okay, so there's when you're talking about things that are rotating, the right-hand rule is something that you're going to encounter next semester too, in a different context. But there's two versions of the right-hand rule, or two kinds of right-hand rule, two right-hand rules that are applicable in different situations, and they're called the right-hand rule because they involve your right hand. So when it comes, all right, I'm back. I don't know why I got disconnected. Okay, so when you're talking about the right-hand rule for something that's rotating, think about it this way. Like, imagine that you were going to grab the axis of rotation with your right hand, and you do it in a way so that the fingers on your hand curl around the axis of rotation in the sense of rotation. So if there's a wheel that's spinning this way, I'll grab it with my right hand so my fingers curl around in the same direction. The fingertips are like the point, the arrowheads, curling around in the same direction. And then your thumb points in one direction or the other along the axis of rotation. Either points up or it points down. So you look at this picture. All right, Bonnie and Clyde are on this merry-go-round, and here's the axis of rotation. So imagine grabbing that axle with your right hand so that your fingers curl in this direction along with the sense of rotation. It tells you right here it's rotating, if you're looking down from above, it's rotating clockwise. All right, and then what direction does your thumb point? Think you got to figure it out? So I grab that wheel with my fingers curling around in the direction of rotation, which is clockwise looking down from above, and my thumb points down. Okay, so the direction of the omega vector in this problem would be pointing down. All right, same question, but now it's not about angular velocity anymore. It's about linear or tangential velocity. Let me clear the poll and vote when you're ready. Who has a larger tangential speed? I think you'll find it useful to think about units. Units of angular speed or angular velocity are radians per second or revolutions per second. But when it comes to linear speed or tangential speed or velocity, what are the units? It would be meters per second. So who has the larger linear speed in meters per second? All right, you guys love B. Which is the correct answer. So linear speeds are not the same as angular speeds. The linear speed is actually a product of radius. So Clyde would have about half the angular or half the linear speed as Bonnie because his R is only about half as much. So, if you think about, a concrete example here, if the radius of this merry-go-round is 2 meters, then Bonnie is going to go around the circumference, which would be 2 times the radius, 4 pi meters every 2 seconds. Clyde, on the other hand, who's only out here at 1 meter radius, would go around 2 pi meters every 2 seconds. So Clyde's linear velocity or tangential velocity is exactly half of Bonnie's. He doesn't have to travel as far to make 1 revolution. All right, you guys are doing pretty good. I'm clearing the results. Question about torque. 2 forces produce the same torque. Does it follow that they have the same magnitude? They, meaning the forces. 2 forces produce the same torque. Does it follow that they have the same magnitude? Your tallies are coming in. Somebody voted for E. And I guess, there's really 2 answers here. It's not worded the best. Here we go. No is probably the best answer, but I guess you could say it depends because torque depends on 2 factors. It depends on back. Come on. One second. Yay. All right. My computer went to sleep. So torque it's a vector, and it's this cross product between R, the distance from the axis of rotation to where the force is applied, and F. So, if you've ever been, if you ever try to loosen a nut with a wrench, right? And, you're trying really hard to loosen this nut. You exert a force, right? You grab it and exert a force to try to rotate this nut, and it doesn't budge. What do? In the real world, you're trying to loosen a nut and it won't come loose. You're trying to loosen a bolt and it won't come loose. Well, what I do is see if I have a longer wrench or socket. I guess there's two things you could do. You could go to the gym and lift weights. So you could try to make F bigger, or you could just go get a longer lever, a longer wrench. And so what you're doing, if you want to increase torque, there's two strategies. You can increase F, or you can increase R. Okay, so this is, I don't know if I mentioned this last time, but this cross product, which you can think of this as the magnitude of R and F times the angle the sine of the angle between them. So sometimes this magnitude is simply referred to the R, the distance R times the sine of the angle, which in the way I drew it here, in both cases is 90 degrees, but it doesn't have to be. This is sometimes written as just R perpendicular, and it's called the lever arm. And let me draw another situation. So all right, the same scenario. You got a nut that you're trying to loosen with a wrench, but instead of pulling perpendicularly or pushing perpendicularly, let's say you push at an angle. So F is at an angle relative to R. All right, so these two vectors make an angle relative to one another. Well, I guess I could draw it here or here. And what is that? Well, it's like if you take the force vector and just sort of extend it, a line through it. What you can do is you can imagine that there is now a perpendicular line between the axis of rotation and that line that goes to the force. Okay? And if you think about the geometry here, the length of this line right there is the same thing I was calling R perpendicular up there. It's equal to R times the sine of theta. Well, that's weird. Okay. It's the side that this triangle I drew in here is a right triangle, and this side labeled R perpendicular is the hypotenuse times sine theta. So in other words, when it comes to torque, what matters, this R sine theta business, is telling you that what matters is not the distance from the axis of rotation to where the force is applied, but the distance from the axis of rotation to that line along which the force is applied perpendicularly, the perpendicular distance. And so that's why this thing, torque, is maximized if you make that angle 90 degrees. That's the angle that maximizes the lever arm. if the angle between the vectors is 0, the lever arm is 0. So you don't get any leverage. Don't get any leverage. Okay. All right, next question. So here's the situation. Let me clear the poll. All right, it's clear. You can vote when you're ready. In which of these cases, three forces, F1, I don't know where F2 got to, but it's not here, F3 and F4, all these forces, so this is like the same person pushing three different ways on the same door. Which of these cases will the torque generated be the greatest? Which of these cases will the torque Well, I got only 3 votes, but you all picked the same answer. All right, let's go on then. And you all picked A, F1. So yes, F1 is going to result in the greatest lever arm because the force is exerted perpendicular to the door. So, one of these will give you 0 torque, F4. You can't rotate if you exert a force that is pointing at the axis of rotation. All right, how large would the force have to be for F4 to be effective? You'd break the door before you got it to rotate. So there is no force that would make F4 effective. All right, next question. So, suppose that you have a speedometer in your truck and it's designed to measure the linear speed of the truck. But what it's actually doing is measuring an angular speed of something in the engine. The engine is lots of parts that move, and lots of those parts are rotating. So this device actually measures angular speed of the tires. And then what you do is you go and you then switch out your tires on your truck for larger tires. How's that going to affect your speedometer readings? What's that going to do? E is not an answer. Who keeps picking E? It's like something my daughter would do. She's a little Nixie. Someone changed their answer from E to D. Okay, all right, moving in the right direction. So, all right, let's see, what do you guys like? You really like B, all right. B is the best answer here. And so it's this radius connection between these two quantities. Angular velocity, angular speed, multiplied by the radius gives you linear speed. So for a given angular speed, which is what this device is ostensibly measuring, a larger tire would correspond to a larger linear speed, V. So you're now, if you say you had, the small tires versus the large tires, but they're both reporting the same speed, the same angular speed, the one with the larger tires would actually be moving faster in a linear sense. Another way to think about this is the vehicle travels a certain distance for every rotation of the wheels. And if you have bigger wheels, that distance is larger. So if you rotate one time every second, have an angular speed of 1 revolution per second, 2 pi radians per second, a bigger wheel is going to translate to a larger linear speed. So the speedometer is not going to be correct anymore. It's going to read a lower speed than the true linear speed of the vehicle. I'm curious, maybe somebody out there knows, is this how actual vehicles work? Do actual vehicles estimate your speed based on the rotational speed of something in the car? I think they do, or at least they used to. In which case, putting on larger wheels is going to change the way your speedometer works. All right, got a few more here. Here are 4 scenarios. Wrenches trying to loosen a rusty nut. Which arrangement will be the most effective in loosening the nut? All forces. So this is like the same person trying to loosen this nut using a wrench. Which is going to be the most effective? All right, you guys have converged on the theory that number 2, on the solution, that number 2 is the best. So B, you're selecting B, number 2, which is the correct answer. Why? Because number 2 has the longest lever arm. It's the same force, but it's exerted much further away from the wrench, from the nut. So it's going to generate the most torque. So actually, number 1 and 4 would be identical, because you have, I don't know if you've ever done this, but I've definitely done this. If I can't loosen a bolt or a nut with a wrench, what I'll do is I'll look for a longer wrench, or sometimes I can sort of link, if I'm using like a box wrench, I can link them together. I can link 2 wrenches together to effectively get a longer lever. Or you can look for like a piece of pipe and put the pipe over the end. So this rod here is like a pipe that you put over the end to extend the wrench. But 1 and 4 would give you exactly the same result because they have the same lever arm. Over here, you say, well, the distance from the nut to where the force is applied is greater over here, but that's not what matters. What matters is the perpendicular distance, which is exactly the same in the 2 cases. All right. All right, here's a question about rotational inertia, moment of inertia. So you have 2 spheres that have the same radius and equal masses. One is made of solid aluminum and the other is made of a hollow shell of gold. Which one would you rather own? No, that's not the question. Which one has a bigger moment of inertia about an axis through its center? Same mass, same radius, one solid, the other's hollow. Which one has a bigger moment of inertia, a bigger rotational inertia? We talked about this at length a few days ago. You guys are hesitant on this one. You only got a handful of votes. All right. Well, still, those of you who have voted, 2/3 of you are correct. Oh, sorry, I take that back. 2/3 of you are not correct. All right, you ready for the reveal? Here we go. Which one has a bigger moment of inertia? It would be the hollow gold sphere. All right, the hollow gold sphere. What's going on here? So remember, rotational inertia is a product of how much mass you have, but also how far away that mass is from the axis of rotation. So in these two scenarios, you have the same total mass, but the fact that one of them is hollow means more of that mass is concentrated around the outer edge of the sphere. So the hollow gold sphere is going to have a larger rotational inertia because more of its mass is further away from the axis of rotation. Okay? Yes, they both have the same total mass and the same radius, but the radius of the sphere isn't what matters. What matters is how far away each little tiny piece of mass is from the axis of rotation. So the gold sphere has a larger rotational inertia. That's a question about rotational conservation of angular momentum. Both of these questions are. All right, so we'll have to save those two for Monday. All right, so that's it for today. And all these materials are posted, and I have all of your. Don't forget to finish your last laboratory activity, and then next week there'll be a laboratory exam, which will really be there'll be a quiz, there'll be a collection of questions about that are relevant to the work you did in lab this semester, and then there will be 2 activities for you to perform. One of them is really cool. You're going to use a video of Commander, what was his name? David Scott. I think his name is David Scott. On Apollo 15, he's standing on the surface of the moon, and he does Galileo's experiment where he drops 2 objects, a hammer and a feather, and they accelerate at the same rate because there's no air drag on the surface of the moon like there would be on the surface of the Earth. But they don't accelerate at 9.8 meters per second squared because the acceleration due to gravity is different on the moon. So what you're going to do is, from this video and some information that I was able to dig up about the hammer, the tools that he's using, and using tracker, you're going to calculate the acceleration due to gravity, determine the acceleration due to gravity on the moon. Anyway, I think that's a fun activity. All right, I will see you. You guys have a good weekend, and I'll see you Monday. We'll talk about angular momentum and wrap up the semester. All right.